to this section of the course where we will be discussing Newton-Raphson method. Raphson method. Welcome to this section of the course where we will be discussing Newton-Raphson method. This method is also known as the gradient descent in computer science, and it's highly used in situations where functions are written in terms of multiple variables, and they are difficult to solve algebraically. Therefore, the computers use this method called the gradient descent, and that's one variation of the Newton-Raphson method. Now, Newton-Raphson method is an iterative example where we evaluate the function, we descend down to x2, we evaluate the function at x2 using the gradient of the function, because the gradient will hit the x-axis, we know where the gradient will hit the x-axis, and we evaluate the function again and again in iterative manner, and we get closer to the root of the function. Now the function in our cases is almost always one variable, so we don't have to worry about any other variables except x. As I said again, let's look at the formula and how it works and where the formula comes from. You can find this formula in the formula booklet, but it's good to understand how it's come about. From our previous work, we know that the gradient of a function is nothing but change of y divided by change of x. What that means is that we evaluate the function at f of x1 and evaluate the function at f of x2, and we divide by change of x. Now, if you look at the graph, we know that x2 is where the gradient curve will be zero. Okay, so the tangent at point A will be zero at x2 here. Okay, so what we do is we are going to substitute f of x2 to be zero into this function here. So we are going to set this to zero and see what happens. What we will get is f dash of x1 will equal to f of x1 over x1 minus x2. Now then you can the denominator swap the denominator with f dash of x. I'm gonna use a PowerPoint to show you what's happening. So we'll get this situation going on, and we can swap around f dash of x with the denominator there. So we'll have x1 minus x2 on the right side of the equation. Then we can simply say x2 will be our next input for the iteration. So we can swap around x2 with the fraction on the left. And what we end up with is this expression here. Now, instead of x2, we know that at each and every step, if we put x1 here, x2 comes out, and we feed that back in there, and we get x3 and so on and so forth. What's going on graphically is shown you above. We are repeating this process until we converge to the answer where there is no more change, and our formula comes to the same answer again and again, no matter what. Now the iteration continues until f of x will be naught, and these two values no longer change. When f of x is zero, this fraction is zero, and the next iteration will give you the same answer as the previous iteration. So when you see the answer changing, the answer stops changing, that's when the iteration has come to an end, or you've reached the result. Now, this method does have a caveat. Let's see why. You calculate the gradient because we are. Let's look at the formula again. On top of the page you see f dash of x in the top left corner. F dash is the denominator here. That means we are dividing by the gradient function evaluated at some value for x. Let's say we are here and we get closer and closer to where the tangent has gradient of 0. Let's say the next iteration is where the tangent line is flat and we have a gradient of 0. Can we divide by 0? There is a turning point here, and unfortunately our formula will give us an error. We cannot evaluate the gradient function at where the gradient is 0. Therefore, that's the caveat of Newton-Raphson method. So, we are asked in this example, let's read this example carefully. We have a cubic polynomial called f of x. The point A with x coordinate p is a stationary point. What's the meaning of a stationary point? It means that f of x, f dash of x is equal to 0. That's the definition of a stationary point. Its x coordinate will give us the gradient is 0. So the equation of f of x is 0 has a root at alpha in the interval of 1.5, 1.8 and 1.9. So in the first part of the question, part A, we are to explain why x naught, or the initial value of p, is not a suitable value to be used to approximate and find the root of the cubic equation. There's not much to add here than to say that where the gradient will be 0 and we cannot divide by 0 in our in our formula. Therefore, Newton-Raphson formula would not work. Part of the question, we are asked to use x naught to be 2 as the first approximation to alpha and apply the Newton-Raphson method to produce after 2 iterations. Note that they told you just to stop after 2 iterations twice. So, what we need to do is figure out the function for the derivative. The f dash will be, let's look at it carefully, differentiating x cubed will give us 3x squared, differentiating 2x squared will have 4x, and minus 5x will give us minus 5. What we need to do is write the formula nice and neat as we would. We are going to substitute value of 2, storing value of 2 on our calculator first. Then we are substituting and writing the formula. What you're going to type in the calculator is answer, because we have to start with x naught. Then you type in the on your calculator a fraction button. On top of the fraction, you'll have to press answer cube plus 2 times answer square minus 2 times answer minus 4, and in the denominator you're repeating that but with the derivative function. So you are writing 3 times answer square plus 4 times answer square without the square minus 5. So this is a quicker way of evaluating the 2 iterations. First iteration should give you a value of 1.86 and second iteration should give you a value of 1.856. Shown you at the bottom of this page. Using the answer key, it makes your work much lighter. C of the same question, we are told, by considering the change of sign in f of x over an appropriate interval, to show that the answer to part B is an accurate answer to 3 decimal places. Therefore, we are to pick a number of 4 decimal places. What we need to do it's best to add and subtract 0.0005 so that we'll have a number just above what's being told in as x2 and just below what it is as x2. Substituting those values into the original f of x will give us these answers. One will be a negative and one will be a positive. Change of sign is good enough reason for us to believe that the root of the polynomial is in fact very close to 1.856 up to 3 decimal places. Happy practicing this section. I'll see you in the next video.